Lecture Notes on Elementary Topology and Geometry by I. M. Singer and J. A. Thorpe. Chapter 1. Some Point Set Topology. 1.1. Naive Set Theory. We shall accept as a primitive, undefined, the concept of a set, collection, family, of objects, and the concept of an object belonging to a set. We merely remark that, given a set S and an object X, we can determine if the object belongs to, is an element of, the set, written X a member of S, or if it does not belong to the set, written X is not a member of S. Definition: let A and B be sets. A is a subset of B, written A is a subset of B. If X is a member of A implies that X is a member of B. A is equal to B, written A equal B, if A is a subset of B and B is a subset of A. Notation: the empty set, that is, the set with no objects in it, is denoted by the empty set. Remark. 1. The empty set is a subset of A for all sets A. 2. The empty set is unique, that is, any two empty sets are equal. For if empty set 1 and empty set 2 are two empty sets, empty set 1 is a subset of empty set 2, and empty set 2 is a subset of empty set 1. 3. A is a subset of A for all sets A. Definition: let A and B be sets. The union A union B of A and B is the set of all X, such that X is a member of A or X a member of B. Written A union B equal the set X such that X is a member of A or X is a member of B. The intersection A intersect B of A and B is defined by A intersect B equal the set X such that X is a member of A and X is a member of B. Similarly, if L is a set collection of sets, the union and intersection of all the sets in L is defined respectively by the union of all sets S a member of L equal the set X such that X is a member of S for some S a member of L. The intersection of S a member of L equal the set X such that X is a member of S for every S a member of L. If A is a subset of B, the complement of A and B, denoted A prime or B minus A, is defined by the complement of A is equal the set X a member of B such that X is not a member of A. Theorem 1. Let A, B, C, and S be sets. 1. A union B equal B union A. 2. A intersect B equal B intersect A. 3. The quantity A union B union C equal A union the quantity B union C. 4. The quantity A intersect B intersect C equal A intersect the quantity B intersect C. 5. A union the quantity B intersect C equals the quantity A union B intersect the quantity A union C. 6. A intersect the quantity B union C equal the quantity A intersect B union the quantity A intersect C. 7. If A is a subset of S and B is a subset of S, then the quantity A union B complement is equal to A complement intersect B complement. 8. If A is a subset of S and B is a subset of S, then the quantity A intersect B complement is equal to A complement union B complement. 9. If L1 and L2 are two sets, collections of sets, then the union of sets in L1 union with all sets in L2 is equal to the union in all sets of L1 union L2. And the intersection of all sets in L1 intersected with the intersection of all sets in L2 is equal to the intersection of all sets in L1 union L2. 10. For L1 and L2, as in 9, the union of all sets in L1 intersected with the union of all sets in L2 is equal to the union of the intersection of S1 and S2 for all sets in S1 and all sets in S2. Proof: the proof of this theorem is left to the student. Definition: let A and B be sets. The Cartesian product A cross B of A and B is the set of ordered pairs A cross B equal the set of A comma B, such that A is a member of A and B is a member of B. A relation between A and B is a subset R of A cross B. A and B are said to be R related if A comma B is a member of R. Example, let A equal B equal the set of real numbers. Then A cross B is the plane. The order relation x less than y is a relation between A and B. This relation is the shaded set of points in Figure 1.1. Definition: a relation R is a subset of A cross A is a partial ordering if 1. The pair S1, S2 is a member of R, and the pair S2, S3 is a member of R, implies that the pair S1, S3 is a member of R, and 2. The pair S1, S2 is a member of R, and the pair S2, S1 is a member of R, implies that S1 is equal to S2. A relation R is a simple ordering if it is a partial ordering, and in addition, 3. Either the pair S1, S2 a member of R, or the pair S2, S1 is a member of R, for every pair S1 and S2 a member of S. The order relation for S equal real numbers is an example of a simple ordering. In general, we say that S is partially ordered, simply ordered by R. Definition: let A and B be sets. A function f mapping A to B, denoted by f mapping A to B, is a relation f a subset of A cross B between A and B, satisfying the following properties. 1. If A is a member of A, then there exists B a member of B, such that A comma B is a member of F. 2. If A comma B is a member of F, and A comma B1 is a member of F, then B is equal to B1. Property 1 says that the function f is defined everywhere on A. Property 2 says that f is a single-valued function. Notation: let f be a function mapping A to B. By f of A equal B, we mean the pair A comma B is a member of F. Definition: let f be a map from A to B. F is surjective onto if for each B a member of B, there exists an A a member of A, such that f of A is equal to B. If f is surjective, we write f of A equals B. F is injective, 1-to-1, if f of A equal f of A sub 1, implies that A is equal to A sub 1. If f is both surjective and injective, we say that f is a 1-to-1 correspondence between A and B. Definition: a set A is countable if there exists a 1-to-1 correspondence between the set of all integers and A. A set A is finite if, for some positive integer n, there exists a 1-to-1 correspondence between the set 1, n and A, in which case we say A has n elements. Theorem 2. If A is equal to A sub 1, A sub n is a finite set of n elements, then the set of all subsets of A has 2 to the n elements. Proof: consider the set F of all functions mapping A to the set yes, no, consisting of the two elements yes and no. F has 2 to the n elements. The set L of all subsets of A is in 1-to-1 correspondence with F. For let F equal a map from L to F be defined as follows. For B a member of L, that is, for B a subset of A, f of B is that element of F, that is, f of B a map from A to yes or no, given by f of B of x is equal to yes if x is a member of B, no if x is not a member of B. F is injective because if f of B equals f of C, then f of B of x is equal to f of C of x for all x a member of A. Thus f of B of x equal yes if and only if f of C of x equals yes. That is, x is a member of B if and only if x is a member of C. Thus B is equal to C. F is surjective because every function g mapping A to yes, no determines a subset B of A by B equal the set X such that g of X is equal to yes, and F of B is equal to g. Notation. Motivated by this proposition, we denote by 2 to the A power the set of all subsets of A. Given two sets A and B, B to the A power denotes the set of all functions mapping A to B. Definition. Let F be a member of the functions from A to B. The inverse, F inverse of F, is the function 2 to the B power mapped to 2 to the A power defined by F inverse of B sub 1 is equal to set a member of A such that F of A is equal to B sub 1, with B sub 1 a subset of B. B inverse B sub 1 is called the inverse image of B sub 1. Note that F inverse is a member of the quantity 2 to the A power to the quantity 2 to the B power. Notation. Let W be a set and let L be a collection of sets. We say L is indexed by W if there is given a surjective function phi mapping W to L. For W a member of W, we denote phi of W by S sub W and denote the indexing of L by W as the set S sub W indexed with W a member of W. Definition. Let the set S sub W be indexed by W. The product of the sets S sub W indexed by W is the set pi of S sub W indexed by W equal the set F such that W is mapped to the intersections of S sub W such that F sub W is a member of S sub W for all W a member of W. If the set W is not finite, this product is called an infinite product. Note that this notion of the product of sets extends to the notion of the product of two sets S sub 1 cross S sub 2, for let W equal the set 1, 2. Let L equal the set of S1, S2, and let phi map W to L by phi of J equal S sub J, J equal 1, 2. Then S sub 1 cross S sub 2 is equal the set of pairs S sub 1, S sub 2 such that S sub J is a member of S sub J, and the product pi indexed over W of S sub W is equal to the set F such that the pair 1, 2 maps to S sub 1 union S sub 2 such that F of J is a member of S sub J, which can be identified with the set F of 1, F of 2 such that F of J is a member of S sub J, which can be identified with S1 cross S2. Remark. The product of sets S sub W is a set of functions. One might ask whether there exist any such functions. That is the product of sets S sub W not equal to the empty set? In other words, given infinitely many non-empty sets, is it possible to make a choice of one element from each set? It can be shown in axiomatic set theory that this question cannot be answered by appealing to the usual axioms of set theory. We accept the affirmative answer here as an axiom. Axiom of choice. Let S sub W be sets indexed by W. Assume S sub W not equal the empty set for all W a member of W. Then the product of sets S sub W is not equal the empty set. The axiom of choice is equivalent to several other axioms, one of which is the following. Maximum principle. If S is partially ordered by R and T is a simply ordered subset, then there exists a set M such that the following statements are valid. 1. T is a subset of M is a subset of S. 2. M is simply ordered by R. 3. If M is a subset of N is a subset of S, and N is simply ordered by R, then M is equal to N. That is, M is a maximal, simply ordered subset containing T. Analytic Conics by Barry Spain, Trinity College, Dublin, May. Published by Pergamon Press, London, 1957. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.